Okay, so in our last class we were looking at how to do this Routh Huwritz criterion. So let's just revise that before we go ahead. So to find or for doing the Routh Huwritz criterion, we need to firstly find the closed loop transfer function T of S. Now there are some subsections in this first step, which is if T of S is given, then we need to choose the denominator of T of S, and that is called the characteristic equation. Now, some questions give us the characteristic equation from the start, so then we can directly use that characteristic equation. But in cases where you're given the open loop transfer function, we first need to calculate the closed loop transfer function before we can do the Routh Huwritz criterion. Second step is to create the Routh table. Then we need to populate the Routh table using our Cramer's rule. Then we need to analyze the first column and we need to look for sign changes in the first column. So this is what we did in the previous case. There was a problem that I had given that you should try and solve. I'm assuming everyone did get the answer to this. So this is the right answer for that question. So please run it through and check if you have indeed managed to get the correct answer. Now that being done, we go on to the special case of a Routh Huwritz criterion. The first special case is if you have a zero in the first column. So when you have a zero in the first column, you need to have a special method of doing your work. So the question that we have given here is s raised to 5 plus 2s raised to 4 plus 3s cubed plus 6s squared plus 5s plus 3. So let us start by populating the Routh table in this instance, and then we can try and see if we can we can identify the special case. So as a first step, I've created the Routh table. Since it starts at s raised to 5, I've got all the terms from s raised to 5 all the way up to s raised to 0. Then the first term is, we're going to write all the odd terms here. So this is where the odd terms are going to be. So it will be the coefficient of s raised to 5, which is 1, the coefficient of s cubed, which is 3, and then the coefficient of s, which is 5. Then in the second row, which is the s raised to 4 row, this is where we place all the even terms. So the coefficient of s raised to 4 is 2, the coefficient of s squared is 6, and finally you have 3. So this is the first two tables of the Routh table. Now using the Cramer's rule, we need to find out what is the first cell of s to the 3 row, right? So by applying Cramer's rule, you will see that it will be 3 into 2, 6, minus 1 into 2, 6, divided by 2. So it will be 6 minus 6 divided by 2. In this instance, it's 2. So that will be 0, as 6 minus 6 is 0. The second column will be 2 into 5, 10, minus 3 divided by 2. So that will be, so this is the first column, let's call it A. The second column B will be 10 minus 3 divided by 2, which is equal to 7 by 2. And obviously there will be nothing on this side. It will be, there's no terms here, so we can put it as a 0. Now the problem that we have is, if you need to find s squared row, we know that it will be 6 into 0, which is 0, minus 2 into 7 by 2, the whole divided by 0. So as a result, you'll see that everything that follows here will be divided by 0, which in turns would mean that it will be infinite. Now, if it is infinite, then we cannot make any sense of the Routh table that we have, because remember, we are looking for sign changes. And as infinity does not have a sign change, we cannot do any of our calculations going further. So as a result of this, we need to now choose a different method or different approach when we have a situation like this. And that approach is termed as the reverse coefficient method. Okay? So the reverse coefficient method is actually quite simple and straightforward. Let me explain to you how it works. What we do is we take the original characteristic equation, that is this characteristic equation that we got in the question, and we reverse the coefficients. So as you can see here, I'll just write it again. We have s raised to 5 plus s raised to 4 plus s cubed plus s squared plus s raised to 1, and then obviously you have the constant. So the original coefficient of s raised to 5 will be now given to the constant. So it was 1 into s raised to 5, so it will be plus 1. The coefficient of s raised to 4, which is 2, will now go to s raised to 1. The coefficient of s cubed, which was 3, will now go to s squared. The coefficient of s squared will now go to s cubed. The coefficient of s will go to s raised to 4, and the constant will now come to s raised to 5. So based on this, you get a new characteristic equation. And it is going to be using this characteristic equation that you will now create your new Routh table. So as you can see here, we have used this new Routh table, characteristic equation, and created a new Routh table. So the odd terms, the coefficients are 3, 6, and 2. The even terms are 5, 3, and 1. So now it will be 6 into 5, 30, minus 3 into 3, 9, divided by 5, which is 21 divided by 5, which is 4.2. So you can also write it as decimal points. In the second column, it will be 2 into 5, 10, minus 3. 10 minus 3 is 7, and 7 divided by 5 is 1.4. And then you have nothing on this side. Now to find the next column, you say 3 times 4.2 minus 5 times 1.4 divided by 4.2. You get it as 1.3. And you continue to complete the Routh table. Now upon analysis of the first column, once you're done, you will see that there are two sign changes in this system. The first one is when you go from s squared to s raised to 1, and the second one from s raised to 1 to s raised to 0. This means that this system has got 5 roots in total, and in this 5 roots you will see that there are 2 which are going to be on the right hand side because of the sign changes that you have. So the stability of the system, this system is unstable because of the sign changes which indicate that there are poles lying on the right hand plane. Where are the poles located? There are 5 poles in total, and we understand that from the characteristic equation, which is s raised to 5. In those 5 poles, there are 2 sign changes, which means that 2 of the poles are lying on the right hand plane. The remaining 3 will be lying on the left hand plane. So this is how you take use of the first method, which is called the reverse coefficient method. So whenever you're doing a calculation and you see that there is a 0 in the first column, we can reverse the coefficient of the characteristic equation, and after reversing the coefficients, we can then create a new Routh table and continue with our analysis. So the most important thing here to note is you need to leave this Routh table where you got the 0 in the first column, and then you need to continue and then do the second one. So both the Routh tables should be shown on your answer script. In the first one, you should indicate that there is a 0 in the first column, right? So you will say here that in this case you will go back here and you say that no further calculation is possible because of the 0 in the first column, because of this problem. Okay, so that is the first special case, which is having a 0 in the first column. Right, then we move on and we look at a different case. So before we do this problem, let us discuss the second problem, which is the one in which you have a 0 in the second column, also the 0 in the entire row. So this is a special case number 2 for the Routh Huwritz criterion. Let us take this problem and try and see if we can indeed solve it. So this is the second case of the Routh Huwritz criterion. So to make work a lot easier, let us try and do this once more and see if we can indeed solve this answer. So here you'll see that the question is s raised to 5 plus 7s raised to 4 plus 6s cubed plus 42s squared plus 8s plus 56. So this is the characteristic equation of the system. Why do I call it as a characteristic equation? Because it is the denominator of a closed loop transfer function. And the closed loop function is described as T of S. Now if this question was a G of S and I was to find out the T of S, I would first need to calculate what is my D of S, and then I'll have to calculate or determine the characteristic equation, which will be the denominator. So in this case, let us start populating the Routh table. As we mentioned previously, the first row will be the odd and the second row will be the even. That's because this one starts at s raised to 5. So it will be 1, 6, and then 8. That will be the first row. And in the second case, it will be 7, 42, and 56. Now, we did say that if you have a row which can be divided, we can indeed do that to make our calculation easier. So you can see that 7, 42, and 56 are indeed factors of 7. So we can divide this throughout with 7. And when we do that, we'll see that we get 1, 6, and then we have 8. So what I've done here is that I've just striked off 7, 42, and 56 and left these numbers. Even when you're doing your work, please do not rub off the elements that you are dividing. You can just strike it and write the simplified or the divided amount on the side. That is because we need to see what was the process that the system has undergone. Now we've got the simplified rows, so both rows are the same. S raised to 5 is 168, S raised to 4 is 168. Now whenever you have a situation like this, you can automatically assume that the preceding row will be a row of zeros. We can do a calculation just to see. In this case, it will be 6 minus 6 divided by 1, which is 0. In this case, it will be 8 minus 8 divided by 1, which is equal to 0. And then over here, it will be 0 minus 0, which will be 0. Now, this is a special case where the entire row is a row of zeros, or ROZ as it is called. Now this is a challenge, because if the entire row is equal to 0, that means that you can do no calculations further. Remember, in the previous problem that we encountered, we had only one row, one cell which was equal to 0. But in this case, the entire row is equal to 0. Now, when the entire row is equal to 0, we have to resort to a different method. We can no longer reverse the coefficients. Instead, what we're going to do is we're going to take the row just above the row of zeros, and we are going to differentiate that with respect to s. So in this case, the row just above the row of zeros is the s raised to 4 row. As you can see here, it is this row. And if you have a look there, that row is made up of s raised to 4 plus 6s squared plus 8. So this is the row that we have above the row of zeros. Now, the first step here is to take the row above the row of zeros. We have done that. We need to differentiate that with respect to s. So d by ds of s raised to 4 plus 6s squared plus 8. So this will become 4s cubed plus 12s plus 0. So over here, it will be 4, and then it will be 12, and as there is nothing there, it will be a 0. Now you can see that we can even further reduce this one, and we can write it in terms of 1, 3, and 0, right? So for clarity, I'm just going to make this a bit more bigger and write it clearly. So in this case, I am rubbing it off, but I would urge that when you're doing your work, you please refrain from doing that. So it will be 1, 3, and 0. How did we get that? We divided this row by 4. Right, so now let's come to the next row. It will be 6 minus 3 divided by 1, which will be equal to 3. Then it will be 8 minus 0 divided by 1, which is equal to 8. And there will be nothing over here. In the next row, it will be 9 minus 8 divided by 3, which is equal to 1/3. And over here, it will be 0 minus 0 divided by 3, which is equal to 0. And there will be also nothing on this side. And then on the last column, it will be 8 by 3 minus 0 divided by 1/3, which will be equal to 8, if I'm not mistaken. Let's have a look. Let's have a look here with that problem. Yes, it will be equal to 8 over here. So we have indeed solved that problem. So we have completed the Routh table from a situation where the entire row was equal to 0. Right. So this is the method for calculating or populating the Routh table with the two special cases. Now we're going to do a similar problem. We'll see if we can have a look at it in the textbook, and we'll try and solve it from the textbook. So we are in this chapter 6 here, which we mentioned is on the stability. And here is this situation where the entire row is equal to 0. This is the problem that we just solved now. And I want us to now go on to a different problem and explain how we do the analysis. So this is a slightly bigger problem, but I'd like you to challenge yourselves to try and do this one as well, whereby T of S is 20 divided by S raised to 8 plus S raised to 7 plus 12 S raised to 6 plus 22 S raised to 5 plus 39 S raised to 4 plus 59 S cubed plus 48 S squared plus 38 plus 20. So over here, you will see that once they have populated the Routh table, they come to the conclusion that S cubed, that is this row here, that is the row that gives you a row of zeros. So effectively what they have taken is that they have taken the row just above the row of zeros, which in this case is 4s cubed plus 6s plus 0, right? And they have differentiated that row, that is s raised to 4 plus 3s s squared plus 2. They have differentiated that row and they have got 4s cubed plus 6s equal to 0. They have put the 4 and the 6 and they see that that is divisible by 2. So on dividing you get 2, 3 and 0. And based on that they continue their calculations. So in the end, how do you now comment about the stability of the system, and how do you now talk about what is the number of poles and where they are located? So once again, we look at the first row. Now you see that there are two sign changes here. The first sign change is from s raised to 7 to s raised to 6, and the second sign change is from s raised to 6 to s raised to 5. So there are two sign changes. In total, there are 8 poles. But now, what does the row of zeros here do to this problem? So what a row of zeros does is that it implies that there will be poles lying on the j omega axis. So I take you back to the S-plane diagram here. Now we said that the poles can either exist on the left-hand plane, which means that the system is stable, or poles can occur on the right-hand plane, which would mean that the system is unstable. But when you have an entire row of zeros, like we just discussed, those poles will lie on the j omega axis, this exact very same axis. They are not on the left-hand plane and they are not on the right-hand plane. So when that kind of a situation arises, then the system is said to be marginally stable. It is undamped, right? It goes into a state of oscillation. So when we have a row of zeros, we need to take into consideration 3 elements. So these are the 3 elements. How many poles do you have on the right-hand plane? How many poles do you have on the left-hand plane? And how many poles do you have on the j omega axis? Now, another thing that is a challenge here is that when you have a Routh table with a row of zeros, you need to consider it as 2 halves. It will be a half that has occurred after the row of zeros and a half that has occurred before the row of zeros. So here, everything that happened from s raised to 8 to s raised to 4 will be considered as occurrences before the row of zeros, and everything that happens from s cube all the way to s square, s raised to 0, is after the row of zeros. That is why they have spoken about an even polynomial and the other polynomial. So on the right hand plane, from the fourth order below, that is from the row of zeros, you'll see that there are no sign changes. Okay? At the same time, the poles that occur on the j omega axis, their speciality is that the poles on the j omega axis exist in pairs, which means there can never be just the one. If there is one pole on the j omega axis, there will be a conjugate pole on the other side. So it's like plus or minus 2j. So if there is 2, then there will be one on the positive side and the other on the negative side. Now if you have a look in our case here, you'll see that from s cube 1, 2, 3, 4. So that means that there are 4 poles from s cube, that is from the row of zeros, to s raised to 0, which implies that 2 will be lying on the positive side and 2 will be lying on the negative side. For example, it will be plus or minus 2j and plus or minus 4j. So plus 2j plus 4j, minus 2j minus 4j. So they will be existing in pairs, 2, 4, 6, 8, etc. So out of the total number of 8 poles, you will see that 4 of them are already lying on the j omega axis. The remaining 4, which is occurring between s raised to 8 and s raised to 4, we already said that there are 2 sign changes, which means that there are 2 poles lying on the right hand plane, and therefore there will be 2 more which will be lying on the left hand plane. So that is what is expressed here. In the even polynomial, that is after the fourth order, there is nothing on the right, there is nothing on the left, but there will be 4 on the j omega axis. While from s raised to 8 to s raised to 4, there will be 2 lying on the j omega, on the right hand plane because of the sign changes, and 2 lying on the left hand plane. So in total, there is 2 poles on the right hand plane, 2 poles on the left hand plane, and 4 poles lying on the j omega axis. So this is a special case of the second special case of a row of zeros in the Routh Huwritz criterion. Next we come to the point where we find the gain of a system using the Routh Huwritz criterion. So this is a section that will be dealt with when we are doing the root locus, but because it's a very simple concept, I'll explain it here. So the question says, for the closed loop transfer function k divided by s cube plus 18s squared plus 77s plus k, we need to find the gain k for the system so that it will cause and enable the marginally stable system. So we want to find out what is the value of gain k, which is greater than 0, that will make the system to be stable. So this is the open loop transfer function, and using this open loop transfer function, they have created the closed loop transfer function. This is a unity feedback system. So let us try and first of all determine how to calculate the closed loop transfer function. I think we have mentioned that here in our previous class when we were doing the second module, but let's try and do this once again here. So over here you will see that the question says g of s is equal to k divided by s into s plus 7 into s plus 11. This is the g of s. Now, if you have a look at the diagram, you will see that it is a unity feedback system, which means that h of s is equal to 1. Now, the formula for calculating the closed loop transfer function is g of s divided by 1 plus g of s into h of s. So in this case, if we are going to multiply this together, you get this will be equal to k divided by s into s squared plus 18s plus 77. So if you multiply that together, you get k divided by s cube plus 18s squared plus 77s. That will be your g of s. Now, if we are going to use this formula, that is g of s divided by 1 plus g of s into h of s, what does this become? So it will be g of s divided by 1 plus k divided by s cube plus 18s squared plus 77s, and of course h of s is equal to 1 like I did mention here. So upon doing your calculations, you will get this as k divided by s cube plus 18s squared plus 77s divided by s cube plus 18s squared plus 77s plus k divided by s cube plus 18s squared plus 77s. So over here you can see that the denominators of both these terms will cancel out, and you will be left with the closed loop transfer function as t of s is equal to k divided by s cube plus 18s squared plus 77 plus k, as they have shown here and as what we have calculated here. So t of s is equal to k divided by s cube plus 18s squared plus 77s plus k. Now based on this, you need to build a Routh table, and that is what is done here. So the term s cube, s squared, s raised to 1 and s raised to 0 are used for creating the Routh table. And in the odd row, you will see that it will be 1, which is the coefficient of s cube, and then 77, which is the coefficient of s. In the even row, you have 18 and then k. Now, when you do a calculation, you will see that the first row, s raised to 1 row, will be 1386 minus k divided by 18, and the s raised to 0 row will be equal to k. So you can do this calculation here. Now for us to find the row of zeros, what we need to do is we need to take a row of zeros where the value of k should be positive. That is mentioned in this question. You cannot have a value of k which is negative. And this positive value of k should give us a row of zeros. So if you now take this example into the Routh table. So let us try and create this Routh table here. Right. So we have one, let's say that this is the row that we have. Right. So this is the rows that we have. Now, where can we create a row of zeros? Let's have a look. Obviously, this cannot be a row of zeros because both terms are equal to whole numbers. The same applies for s squared row because 18 is a whole number. K can be a zero, but again, the condition is that k should be greater than 0. So it cannot even be equal to 0. Now, if you look at the s raised to 0 row, again, you have k and then you have 0 and 0. So this is a possible row of zeros. But again, the problem is for you to have this as a row of 0, k needs to be equal to 0, which cannot be the case. So we're left with the s raised to 1 row. And in the s raised to 1 row, you have 1386 minus k, and then you have 0, and then you have 0. So if you want to make this to be your row of zeros, you will see that k needs to be equal to 1386. And this satisfies our condition that we need to create a row of zeros with a positive value of k. So we are assuming that this is equal to the row of zeros. So the question here is, what is the value of k that will make the system to be stable, and the one that will make it to be marginally stable? So the answer here is as follows. For this system to be stable, k should be greater than or equal to 1386. Because if k is equal to 1386, it means that you have a row of zeros. And if you have a row of zeros, it means that the system is marginally stable. So this is for marginal stability, and this is for stability. And if there is any value of k less than 1386, then you can say that the system is unstable. So this is how we use the Routh Huwritz criterion to determine the stability of the system. So here once again I've just shown you here the left hand plane, that is where the system is completely stable. On the right hand plane, the system is unstable, and if the poles lie on the j omega axis, then the system is marginally stable. So that brings us to the end of the first part of the third module, which is on the Routh Huwritz criterion. The next part will be looking at the root locus. Okay, right, thank you.